Okie dokie artichoke! Newton's law of universal gravitation. Physics lesson 6.1. Alright, so let's just quickly review the force of gravity. Gravity pulls down with an acceleration of 10 meters per second squared. You know, that's a rounded estimate. But it's not a force. That's the acceleration of gravity. The force of gravity depends on your mass or the amount of inertia an object has, and we call that weight. Now, gravity is a force like anything else. So the amount of force is definitely going to depend on mass, but it's also going to depend on distance. And it kind of works like this. The more mass you have, the more force you have. Less mass you have, the less force you have. This is what we know as a direct relationship. Distance, however, the less force you have, the more distance you are away. And the less distance, the more force. This is an indirect relationship. So one goes up, the other one goes down. Alright, and it's related by this law here, which is the force of gravity is equal to G, which is a constant value. That's the universal constant for gravity. This holds true throughout the universe, and that is 6.67 times 10 to the negative 11th. And we'll use that in substitution of G for all universal gravity equations. So mass 1, that's the mass of your first object, and mass 2, that's the mass of your second object, and it doesn't really matter what you choose to be mass 1 or mass 2, because 5 times 1 is the same as 1 times 5. And then the distance is measured in meters, and that is meters squared. Alright, so let's do a quick practice problem. So let's say we have Deimos. Deimos is one of 2 moons of Mars. The other one is Phobos. It has an average radius of 6.3 kilometers. If the gravitational force between Deimos and a rock, hello rock, is 2.5 times 10 to the negative second, then what's the mass of the moon? Well, let's go ahead and figure this out. The first thing we need to do is set up our problem. So I'm going to try to squeeze it in over here. 2.5 times 10 to the negative 2 newtons. That it should equal G, which is 6.67 times 10 to the negative 11th, multiplied by mass number 1, which is 3. And we're looking for mass number 2. And again, it doesn't matter which one you choose as mass 1 or mass 2. It's going to end up being the same. So, distance 6.3 kilometers. But it needs to be in meters. So that means we need to take that 6.3 kilometers and convert that to meters. So every 1 kilometer, there is 1,000 meters. So that gives us 6,300 meters, and that is squared. Now, when you are working these equations, be careful and use parentheses when able. These exponents, those are some tricky buggers. Alright, if you don't put these in parentheses, your calculator is going to do some fun things with order of operations that you're not going to want it to do. And overall, you should end up with 5 times 10 to the 15th kilograms. Alright, that concludes 6.1. Most of your universal gravitational problems are going to involve this equation and some variation of 2 masses and a distance. So hopefully that's helpful. If not, well, poop, I'm sorry, and I'll see you next time.